Our process began with a detailed CAD modeling, where the axe geometry was designed for both performance and manufacturability. Using Microsoft simulation, we evaluated metal flow and solidification behavior to identify potential defect regions and optimize our gating strategy. During this step, careful attention was given to part orientation and spacing. Each axe was positioned individually along the sprue, with one part on each side, to promote smooth, directional metal flow while minimizing turbulence as the mold fills. By controlling the way metal enters each cavity, we reduce the likelihood of defects such as air entrapment, misruns, and cold shuts. The connection points between the part and the sprue were also designed to allow for efficient feeding during solidification, helping compensate for shrinkage and improving internal soundness. Here are 4 trees as shown, demonstrating the use of both polycast patterns and traditional wax 3D print patterns. The assembled tree then underwent ceramic shell building through repeated slurry dipping. Molten metal was poured into the ceramic molds under controlled conditions. Preheating the mold reduces thermal shock and allows the metal to maintain fluidity longer, improving its ability to fully fill the cavity before solidification begins. Following solidification, the castings were removed from the sprue system, separating each axe from the primary gating structure. After this initial separation, non-destructive testing was performed using X-ray imaging to evaluate the internal integrity of these castings. Once internal quality was verified, the remaining gates were removed and the castings underwent initial grinding and surface refinement. By performing a majority of grinding in a softer as-cast condition, we minimize the risk of overheating the material and preserve the desired microstructure. The axes then underwent a carbon restoration followed by a mar quench in molten salt to produce a uniform hardness of 52 HRC. The handle fabrication began with selecting white ash from our backyard, a material commonly used for tool handles due to its strength, toughness, and ability to absorb shock. The handle was then shaped and refined entirely by hand, with material progressively removed to achieve the desired profile. Hand sanding was used to smooth the surface and fine-tune the geometry, ensuring a comfortable grip and consistent finish. To further enhance grip and functionality, leather was measured and hand-cut to fit the handle. The addition of the leather wrap improves handling by increasing friction and comfort, while also contributing to the durability and overall finish of our final piece. Finally, the wood was stained with teak oil. The axe head then underwent polishing to achieve a mirror finish, significantly refining the surface and creating a highly polished appearance. This process enhances the overall visual quality of the part while producing a smooth and consistent surface. In addition to the axe head, the langettes were also polished to maintain a uniform finish across all visual components. Following polishing, electroplating was selectively applied to the Wisconsin insignia on the axe. With all components completed, the axe head and handle were assembled to form the final product. Careful attention was given to the fitment and alignment to ensure proper balance, stability, and reliable performance during use. A secured connection between the handle and the head is critical for both functionality and safety. The design of the horseman's axe draws from historical tools known as versatility, influencing both the geometry and overall functionality of this final piece. These tools were traditionally designed for efficiency and adaptability, which guided many of our design decisions. Once assembled, the axe was put to use to evaluate its performance under real conditions. Testing focused on durability, edge retention, and overall functionality, allowing us to assess how the axe responds to repeated use and loading. This step ensures that the final product is not only visually refined, but also capable of performing as a practical and reliable tool. This project aligns with the goals of the Cast and Steel competition, which encourages students to explore the production of steel components through casting while applying modern engineering tools and techniques. From initial design and simulation to casting, finishing, and final assembly, each stage of this process was intentionally developed to control quality and performance. Together, these efforts demonstrate the successful integration of materials engineering, manufacturing processes, and craftsmanship into a complete final product.